Hello, and welcome back to the course on Physics for Engineers. We are still on chapter 13 of this course, the chapter on magnetostatics. So before we proceed with this lesson, let us first review some concepts. So in the previous lesson, we have defined that moving charges and current are the sources of magnetic field. And we have this equation to solve for the field of a moving charge and a current carrying the conductor. The second equation being the law of Biot-Savart. And it all depends on the cross product between Q V cross R for moving charge and I cross R for a current carrying conductors. So again, you should review your cross product relationships using the right hand rule. So if your vector A is your pointing finger and vector B is your middle finger, then A cross B will be your thumb. So for this lesson, we will be discussing about magnetic force, which will be on moving charges and current carrying conductors. So in the same manner as in the same pace as we have in when we discuss the sources of magnetic field, we start with the magnetic field of a moving charge. Now we will try to find what is the magnetic force on a moving charge due to an external magnetic field. So the magnetic field, if you have a moving charge Q with velocity v, say it's moving to the positive x-axis, and there's an external magnetic field. Take note that this magnetic field is not the magnetic field of your moving charge. Take note, this moving charge also has its own magnetic field. And if you place it in an external magnetic field, so the magnetic field of this moving charge will now interact with the external magnetic field. And that will create a force, a magnetic force. So magnetic force is basically just the interaction between the magnetic fields of two different magnetic materials. So you can think of the force like that. So the force on the moving charge, moving with velocity v, will be this one, qv cross the external magnetic field. So of course, if you take the magnitude of that, the magnitude of this is qvb sine phi. Since this is a cross product, so sine phi. And to get the direction, you use right hand rule. So again, if in this case your velocity of the charge is moving to the positive x-axis, and your external magnetic field is into the pitch. So that one. So the magnetic field is into the pitch. So V cross B. Sorry. The velocity here will be your first vector. If you use right hand rule, the velocity is your pointing finger. The magnetic field is your middle finger, and V cross B, the force, is your thumb. So this is V, your pointing finger, the first vector. B, the magnetic field, your middle finger, and V cross B is your thumb. So in this case, if you V cross B, uh, the magnetic field is inside into the page. It's quite hard actually. So actually the force here is upward. So this is the V. This is magnetic field. It's into the page. So therefore this is V cross B or the force. So the force here actually upwards. So you use V cross B if it's use right hand rule if the force is positive. Oh, sorry, if the charge is positive, a positive charge. If it's negative, then you have to flip your right hand. Since the negative charge will actually flip the direction of a vector. The negative of a vector is just the vector in opposite direction. So assuming since this is a positive charge, then V cross B is, in this case, upward to the positive y-axis. So in this case, F is actually perpendicular to both the velocity and the magnetic field. So what will happen now in this scenario is that since the moving charge is originally moving to the positive x-axis or to the right, and since there's a force uh, acting on it upward, then the the charge will actually have a curved path. So yeah, it will actually curve. Instead of going straight, since there's a force acting on it upward, then it will curve around. So that's what happened to its path. Okay, let's test your no. So what if you have an external magnetic field? This is external, external magnetic field. It's out of the page, and then you have a moving charge going to the left. What is the direction of the magnetic force? So you just V cross B. That one, V cross B. So your velocity is your fingers, your pointing finger. Your magnetic field in this case is out of the page, so towards you. So therefore, the magnetic force is upward. So we can also use this one. This is the velocity. This is the magnetic field going towards you. So therefore, the magnetic force is upward. So that one. Another example. Magnetic field here is into the page, and you have a moving charge moving quadrant number 1. So V cross B. So V is your pointing finger. Magnetic field is your middle finger. It's into the page. So therefore, the force is this one. So the force will be in quadrant number 2. So just like this one. So this is your V. The magnetic field is going out of the page. So therefore, the force is this one. So this angle is actually 90 degrees. So again, another example, you have an external magnetic field and your velocity is moving upward. So velocity, that is your your velocity is this one. Your magnetic field is into the page, so V cross B. So therefore, the force is to the left. So V cross B. V, your pointing finger. B, the magnetic field is into the page. So therefore, the direction of the force is that one. So to the left. So last example, an external magnetic field pointing out of the page. Moving charge moving upward. So V cross B. So you have the first finger V, and magnetic field is outside. So therefore, the force will be to the left. So that one, no? So V, pointing finger is your velocity. Magnetic field is your middle finger. It's pointing outward. So therefore, the magnetic field is to the, magnetic force is to the right. Okay. So in the event that the velocity of your moving charge is purely perpendicular to the external magnetic field, then your charge will actually undergo a uniform circular motion. So I've mentioned earlier that this charge will actually curve. So it will actually curve and form a circular motion. So at every point, if you will notice, the velocity is perpendicular to the or tangent to the circle, and the force is always going towards the center of the circular motion. So basically, the force here becomes a centripetal or radial force. Centripetal or radial force. So centripetal force, if you will recall, it's mass times centripetal acceleration, where centripetal acceleration is v squared over the radius, v squared over r, the radius of the circular motion. So you can actually relate that to a centripetal force. So on the other hand, if the velocity has both parallel and perpendicular components to the magnetic field, then the motion is a helical motion. So if you have a positive charge, it will undergo a helical motion along the direction of the magnetic field. But if it is a negative charge, it will undergo a helical motion but in the opposite direction of the direction of the magnetic field. Okay, let's have an example of this. A practical example. A practical example of this is the magnetic field of the Earth. So the magnetic field of the Earth protects us from charged particles from the sun and other sources around or outside our planet. So if there are positive charges, then the magnetic field of the Earth is from the north magnetic pole here, close to the south pole of the Earth, south geographic pole of the Earth. So the direction of the magnetic field is from the south or from the north of the magnetic pole to the south magnetic pole, which is close to the north geographic pole. So if you have positive charges, they will just spiral around in a helical motion towards the pole. And if you have negative charges, they will spiral around toward the south pole. So this is the magnetic field of the Earth. If it receives a solar flare, for instance, that is a charged particle, a charged radiation. The magnetic field will protect us. Actually, that's the purpose of the magnetic field. It protects us from charged particles. So the particles will just spiral around in a helical motion towards the North Pole and the South Pole, depending on their sign, if it's positive or negative charge. And when they interact with the atmosphere in the north and south geographic poles of the Earth, they form what we call an aurora. Aurora borealis, or northern lights, for those living in the northern hemisphere. For those living in Canada, uh, they see northern lights often. Aurora australis, or southern lights, if you are in the southern hemisphere. So I don't know if people in Australia can see southern lights or aurora australis. Maybe because it's australis. I don't know. So that's a practical application of the magnetic field forces on magnetic field. So it will undergo a helical motion. Charged particles will undergo helical motion when they interact with a magnetic field. So let's now go to the magnetic force on a current carrying conductor. So for a current carrying conductor with length L and carrying a current I and exposed to an external magnetic field B. So I didn't place any word external here, but this is assumed that this magnetic field is external. Take note, a current carrying conductor has its own magnetic field. So this is external. This is not the magnetic field of the current carrying conductor, but external. So what will happen is, if there's a current upwards and there's a magnetic field, it's exposed to a magnetic field, external magnetic field, which in this case it's into the page. So using right hand rule, I is your fingers, B is your magnetic field, your middle finger. Then therefore there will be a force to the right in this specific case. So the magnitude is ILB sine phi, or the integral form of this in the event that you have a non-straight current carrying conductor. You need to integrate IB sine phi dl. So this still obeys the right hand rule. So I is your pointing finger, B is your middle finger, and the force will be I cross B, your thumb. So that's the right hand rule. Okay, so in this figure, you will notice there's a magnet. There's the north pole of a magnet, south pole of another magnet. Therefore, the magnetic field is downwards. And there's a current in the wire being held by this person here. The current is actually, this is X, meaning into the page, or the current is flowing along the direction or into the page. So the current is into the page. The magnetic field is downward. Therefore, the current is into the page. The magnetic field is downward. This is my magnetic field. Therefore, there will be a force to the left. So if you push this wire through this magnetic field here, there will be a force in the opposite direction. And as you see in the comics, it's being rejected again because there's a force in the opposite direction. Okay. So application of real life application of force on current carrying conductors is the speaker. So if you try to dismantle a speaker, I'm not recommending that you do, but if you try to uh, dismantle it, you will actually see a current coil or a current loop and circular magnets. So basically, you have the North Pole magnet and the South Pole circular magnets, and this will be the reason. This will exert a force on your current carrying coil. So this coil will have a signal from your amplifier. So the signal for the current there will be alternating actually. So what will happen is uh, it will exert a force on this coil, and the force will be depending on the direction of the current. The force will be it's either to the left or to the right. So what happens in a speaker is, since the current inside your current passing through your coil will be alternating, so the force will also be alternating. It will be pushed upward and backward. It will be pushed forward and backward. And the forward and backward motion, back and forth motion, as we have discussed in the chapter on waves, this will create mechanical waves and produce sound waves. So that one. So there's a vibration, back and forth vibration due to the magnetic force, and this will create mechanical waves or sound waves. Okay, let's have an example. First, let's test your understanding. So the figure shows a uniform magnetic field pattern into the plane. So that's the external magnetic field. And you have a moving charge, moving with velocity v going to the right. But now, this charge is negative. So which of the three paths does the particle follow? Is it path 1? Will it curve upward? Or it will there be no there will be no force? It will just continue straight. By the way, what's the only way that the magnetic force will be zero if or is when V cross B is equal to zero, and that happens when the velocity and the magnetic field are parallel to each other. So if this charge is moving into the page in the same direction as the magnetic field, then that will experience no magnetic force since V cross B is zero. So V cross B. So V velocity is our pointing finger velocity. Magnetic field is into the page, so this one V cross B. So supposedly, if it's a positive charge, there's a force upward, but since it's a negative charge, so the negative of vector is the reverse. So the magnetic force in this case is actually downwards. So meaning the charge particle here will follow path number 3 because it's a negative charge. If it's a positive charge, it will follow path number 1. So that one. Okay, another example, magnetic force on a proton. So you have protons. They move at 3 times 10 to the 5 meter per second through a uniform magnetic field B, with magnitude of 2 Tesla. And it's directed along the positive z-axis. So the velocity of each proton lies in the xz plane at an angle 30 degrees to the positive x-axis. So find the magnitude and direction of the magnetic force on a single proton. So if you have a single proton and you expose it to an external magnetic field B directed along the positive z-axis, and the proton is moving in this direction 30 degrees with respect to the positive z-axis, then you can calculate the magnetic force using V cross B. So in this case, V cross B, this is our V, the first finger, and B, the second finger. So therefore, V cross B is downward. So in this case, it's along the negative y-axis. So we know that the direction, by virtue of right-hand rule, we already know the direction. It's along the negative y-axis. So we only need to solve for the magnitude. So I'm not going to do a vector approach here. I'm going to go with the magnitude and direction approach. So I'm going to solve for the magnitude first. So magnitude of Q, magnitude of V, B, sine phi, the angle between them, which is 30 degrees. So this is a proton. The magnitude of the charge of a proton is 1.602 times 10 to the negative 19 coulombs. The velocity is 3 times 10 to the 5 given meter per second. Magnetic field is 2 Tesla, sine 30 degrees. The final unit is Newton. As long as all of your units here are converted to standard units. So you will get 4.8 times 10 to the negative 14 Newton. That's the force on the proton, on a single proton, and the direction is downwards or along the negative y-axis. If you want to answer in vector form, it will be 4.8 times 10 to the negative 14 Newton, negative j hat. Negative y-axis, the direction for the negative y-axis is negative j hat. Okay. For the last example, let's have try to find the magnetic force on a curved current carrying conductor. So you have a curved current carrying conductor here. It's actually 3 segments. This is segment number 1. The segment wherein it's perpendicular to the straight segment, and it's still perpendicular to the external magnetic field, which is pointing out of the page. The second segment is a half circle, and the third segment here is basically out of the page. So the current in the third segment is actually going to the into the page, the current. So if, in this case, the current is actually parallel to actually in this case anti-parallel. So their angle is 180 degrees. So meaning, if they are parallel or anti-parallel, then the force here is 0. So since the cross product is 0. So the third segment will have no contribution to the field. Only the first and second segments. So for this first segment here, so we'll call this F, the force on this is F1. So you have I cross B, I cross B. So therefore the force will be upward by virtue of right hand rule. And we can solve for F1 by, for segment 2, that's one, those are the forces on the segment 2. So for segment 1, it's just ILB sine phi. This is the magnitude. We already know the direction. It's upward. So ILB sine phi, phi is 90 degrees, obviously. The angle between the current and the magnetic field is 90 degrees. They're perpendicular. So you will get F1 of 0.2 newtons. Now, for F2, for the second segment here, we need to integrate. So if we designate the upward direction as the positive y-axis, then it's 0.2 Newton along the positive y-axis, or 0.2 Newton j hat. So for F2, we need to integrate. Now, this is basically just my DL here, and there's a component of the DL, which I will call theta. So DL in a cylindrical coordinates are d theta. So if you will notice, for every differential force here on segment number 2, there will be an exactly opposite differential force in the other side of the segment, wherein the x component will cancel out. So the x components of these two vectors will cancel out, and only their y components will contribute. So meaning the force on this whole segment here will also be upward. The x components of this is to the right, the x component of this is to the left, so that will actually cancel each other out. So only the y component will contribute. So again, only the y component will contribute. So the y component of the vector of a vector is actually the sine theta. The cosine theta is the x component. The sine theta is the y component. So only the y component of the vector will contribute. Hence the sine theta here. So rd theta here is the dl, and this is the corresponds to the y component. So only the y component of the force will contribute. So you take the integral of this, and you will get take r out of the integral, and the integral of sine theta d theta from 0 to pi. Since it's only from 0 to pi, it's half of a circle. It's not from 0 to 2 pi, so it's from 0 to 2 pi, 0 to pi, and the answer is 2. And you will get 2 IB. Sine phi is just 1, so 2 IB times r. So you substitute all of that, and you will get 0.8 newtons, and the final direction is along the positive y-axis. So this whole segment here will be forced still upwards towards the positive y-axis. So the final vector now, or the final force, will now be the addition of these three. So since there's no force on segment number 3, being it being parallel to the magnetic field, or in this case exactly anti-parallel, so F1 is only y component, F2 is only y component, and F3 is 0. Then F1, we just need to add their components, the y components. So in this case, you have 0.2 I hat basically, j hat basically, since positive y axis, and 0.8 j hat, and you will get a value of 1 Newton j hat, or 1 Newton along the positive y axis. So that's how you solve this problem. So that's the end of this lesson. And the next lesson will be the last lesson for chapter 13, magnetostatics. And we will discuss the force on a current loop. And I will see you again in our next lessons. Bye-bye.